I've got the graph of cosine up here, and as with any of the trig functions, and in fact any periodic function, it repeats its y values. So it's not one-to-one, and it's going to fail the horizontal line test. Any horizontal line, including the x-axis, which I can see right here, any horizontal line that intersects it infinitely often. So cosine is not one-to-one, and therefore it is not invertible. And so when we talk about the inverse cosine function, and I hate that name, I prefer to call it arccosine, we are not talking about the inverse of this. What we're going to do is exactly what we did with sine. We're going to create a related function that agrees with this function but has a restricted domain, so that we're only getting part of the graph, and we're going to choose a part that passes the horizontal line test and is invertible. And arccosine will be the inverse of that function. Now, as I restrict the domain, I'm going to be working with this graph. I'm also going to be thinking in terms of quadrants. Here, I'm representing my angle on the horizontal axis, and as I move across the axis, it's like I'm rotating through the quadrants if I were representing my angle rotationally. Okay, so I basically want to choose an interval that corresponds to two quadrants. Not every iteration of those quadrants, because of course, quadrant 1 is from 0 to pi over 2, but it's also from 2 pi to 5 pi over 2. And I'm going to choose quadrant 1, but I'm going to choose the nice version from 0 to pi over 2. So I want an interval that corresponds to one iteration of two quadrants, one where it takes on its positive values and one where cosine takes on its negative values. We always choose quadrant 1 and the nice version that contains the acute angles, so from 0 to pi over 2. So that's going to give us this section of graph right here. So this new function that I'm creating is going to agree with cosine over this interval from 0 to pi over 2. And that's where we'll get all of the positive values of cosine. Okay. So then I want to choose an adjacent quadrant, and I want an adjacent quadrant so that I get an adjacent interval, so that I get a connected piece of graph. I want the adjacent quadrant where cosine takes on its negative values. So quadrant 3 is out because it's not adjacent. It wouldn't give me a connected interval. When we were working with sine, we chose quadrant 4, in particular the version from negative pi over 2 to 0. Notice I can't do that here because that would have me repeat the positive values. Cosine is positive in quadrant 4, so I need to choose quadrant 2. And the adjacent version of quadrant 2 would just continue on from pi over 2 to pi. So this is the function I'm going to create. I'm going to make sure I indicate that these endpoints are included as points. They're not holes in the graph there. I don't just suddenly stop. I draw that point and then stop. All right, this is the function I'm going to create that agrees with cosine when it's defined, but only hits each y value once. So this is y equals cosine of x, where x is in the interval from 0 to pi. And I can either express that using this interval notation, or I could use an inequality saying that x has to be strictly between 0 and pi. Or I'm sorry, not strictly between, has to be between 0 and pi using inclusive inequalities. Okay, this is one-to-one. It is invertible. So when we talk about taking the inverse function, that's the function we're taking the inverse of. So let's define that. So y equals arc cosine of x. That's the notation I prefer, but it's equivalent to cosine inverse of x if you prefer that. Just again, make sure you don't think of that as an exponent. This is not the reciprocal of cosine, it's the inverse. Okay, what this means is I'm going to have this, but with the roles of x and y reversed. So I'll have x equals cosine of y. So y is the angle and x is the trig ratio. But I also need to replace the roles of x and y in naming any restrictions. So it also means that y is in the interval from 0 to pi. Okay. What that does is it means that y is the angle in 0 to pi. The angle meaning there's a unique one in this interval whose cosine is x. If I didn't restrict the interval, and I said y is the angle whose cosine is x, well, there would be infinitely many of them. Okay, but there's only one in this interval. Okay, so I find when I'm working with inverse trig that it's much easier to rewrite things in terms of trig, but a lot of times people forget the restriction. Okay, so let's just practice evaluating one of these. Let's say I wanted to evaluate arc cosine of -1/2. So what I like to do is give that a name that reminds me that it's an angle that I'm looking for. And then I'm going to rewrite this using regular trig. So this tells me that cosine of theta is equal to -1/2, and theta is in the interval from 0 to pi. In the next chapter, we're going to be solving equations like this, and we're going to see that there are infinitely many solutions. There's one solution once I have this restriction. Okay, now in evaluating trig functions, I usually do a two-step process. I look at what quadrant we're in to figure out the plus or minus sign, and then I look at what the reference angle is to figure out the absolute value. Well, in working with inverse trig, it's basically that same two-step process, but in reverse. I'm going to use the plus or minus sign, in this case it's a negative sign, to figure out what quadrant we're in. And then I'm going to use the absolute value, which would be 1/2, to figure out what the reference angle is. And then I can put those pieces together. So, if theta has to be between 0 and pi, I know that's either quadrant 1 or quadrant 2. But cosine is negative. That means it's got to be quadrant 2. So I'm looking at a picture like so, where theta is now going to be an obtuse angle. Okay, fabulous. I like to give my reference angle a name. I almost always call it alpha. Okay, and what I know about the reference angle is it's a positive acute angle. If I evaluated its cosine, I would get the absolute value of cosine of theta. Because that's what I do. I use the reference angle to figure out what's the absolute value that I attach to the plus or minus sign. So that would be 1/2. So alpha is the acute angle whose cosine is 1/2. Well, that makes me want to draw a 30, 60, 90 triangle. 1, 2, √3. Some of you may need to draw that to remember what angle it is. Some of you might remember without drawing which angle it is. It's fine either way. The angle whose cosine is 1/2 is 60 degrees, but of course we're working in radians, so I need to convert that to radians. That's going to be pi over 3. So alpha is pi over 3. Fabulous. Now I can look at my picture and I can see that theta is pi minus pi over 3. Because pi would have me rotating this way. If I subtract that extra pi over 3, then I've just done the theta rotation. So notice that's 3 pi over 3 minus pi over 3. That's going to be 2 pi over 3. Fabulous. Okay, so we have answered that question and evaluated our first value of arc cosine. I'm going to put up a couple of problems for you folks to try, and then I suggest you try these before watching the next video. We'll go over them together in the next video. Okay. So I'd like to know what is arc cosine of, let's go with -√3 over 2. And I would also like to know what is arc cosine of 0. And then let's go ahead and graph y equals arc cosine of x and state the domain and range using interval notation. So 3 problems for you to try. Give them a shot, tune into the next video, and check your work.